All right, and so now at this point, after learning about the end behavior of a graph, or also known as the long-run behavior of a graph, it's now time that we head into those other behaviors in the middle part of the graph, in the middle body of the graph, no longer the end behavior of the graph anymore. So we are completely through with the end behavior of a graph, of a polynomial. So now we're going to look at what's going on between the two ends, in the middle body part of the graph of a polynomial. Okay, and so for that reason, quite a few professors in these days, or quite a few textbook authors in these days, we also refer to these behavior as the short run. So as opposites to the long run behaviors would refer to the end behaviors. Now we're looking at the short run behaviors, like those kind of behaviors that happen in the middle body of the graph, okay, of a polynomial. So we are still looking at all the behaviors of a polynomial, both graphically and algebraically. Okay, and so among all of these short run behavior right here, okay, then first thing we want to look at is the intercepts. Okay, so let me now give a brief explanation about what an intercept is, first of all. So now we're going to be studying about the intercept. And so this is completely unavoidable that when we bring up this topic about the intercepts, we have to keep working with the graphs of a polynomial and keep bringing it up side by side. And so at this point, once we see a polynomial as a function, then just like how I delivered this the understanding a long time ago when we started learning about functions, then any function has a graph. So a polynomial at this point, being a function, will have a graph too. Any function has a graph. So a polynomial, no doubt about it, it will have a graph. Okay? And so now the graph for any polynomial is and so in this way, how I'm seeing it, as soon as we know our function has a graph, then as soon as we know our polynomial has a graph, then let me just quickly draw a graph right here. Okay, then a graph can be turning up, turning down. Okay, so there will be a place or multiple places where the graph crosses with the x-axis, or mainly the horizontal axis. So we refer to this, graphically we refer to this as the horizontal. So that point right there where the graph hits the x-axis or the horizontal axis, we call any of those the horizontal, okay, the horizontal intercept. All right, a place like that, because that's where the graph hits any graph, not only polynomial, any graph of a function will or will not hit with the x-axis, the horizontal axis. So we call that the horizontal intercept. Okay, and then just like that, on the y-axis, wherever our graph of the polynomial hits, with the vertical axis here, and yes, we refer to that point here as the vertical intercept. All right, so that's just as far as the naming. That's for now. This name comes straight out from the way how the graph is. The graph for any function, and particularly here the graph for any polynomial. Okay, and so now allow me to quickly bring up a little small demonstration polynomial. It's not a formal example, or it's not even a formal problem. It's just we have to bring up a polynomial to start demonstrating the idea here. Okay, so on my other board space, let's now look at the following polynomial. So allow me to write it down. How about we're looking at our polynomial f of x here as a function. It takes input x, okay, and the rule of this polynomial says for every x input, I'm going to raise that to the third power. All right, minus 7x squared plus 15x minus 9. All right, so this is my polynomial. So now let's quickly apply what we have already learned and understood up to this point. Let's apply our understanding from things, from the earlier understanding right here on this particular lecture still. This is a third degree polynomial, degree 3. Okay, the leading coefficient is a positive 1 right here, and it's an odd degree polynomial. All right, so whatever that is, that's just how we apply our understanding just from the earlier part of this lecture over here. And yes, in that way, optionally, we can also say that this is a cubic because the degree here is degree 3. All right, and it has 4 terms being listed here. So keep in the back of your mind, it will have a graph. Okay, it will have a graph. So you can go ahead and use any of your favorite graphing utilities, including the TI calculators or Desmos I've been using to quickly pull out a graph, and you have learned enough technique how to use your own graphing device to instantly pull out a graph or something like this. Okay, so now on my computer screen, this curve right here is the graph of my function that was written on the board earlier. So this is the curve. And I purposely hid away the numerical labels and all that. I just want to show you the fact that I just want you to enforce the understanding that, so now once we have the graph, this graph will, you see this graph here hits this graph, the graph of our x cubed minus 7x squared plus 15x and minus 7 right here. This graph hits the x-axis, the horizontal axis, at, we recognize 2 points for now. All right, everything is completely based on observing the graph right now. And so I purposely hid away the 2 values here. But so this graph here has 2 the horizontal intercepts. That's how I'm saying it. So just in a way how we are observing the graph right now, I'm seeing this graph has 2 the horizontal intercepts. And then now I'm observing down to the lower part of the graph. This graph has a y-intercept, or now more generally a vertical intercept right here. Okay, so let me now bring up another one. So how about, so aside from this problem right here, how about, let's look at another function. Let's call that p of x. And I'm going to look at, how about x to the 4th plus 4x squared plus 5. Okay, x to the 4th plus 4x squared plus 5. All right, and once again, it's a polynomial. Okay, it's a polynomial. We have already seen from this earlier polynomial that I brought up as a demonstration problem. This polynomial was a degree 3, so now this one here is a degree 4. Okay, and you can call it, it's a quartic if you still remember that way of naming it, but it's completely okay that we don't go with the precise naming here. All I see is it's a degree 4 polynomial. Okay, and so let's look at the graph, and just like how I said earlier, the graph is gonna have at some point some points where it crosses the x-axis, and at some other point it crosses with the y-axis, the vertical axis or the horizontal axis. So let's investigate this function right here, the x to the 4th plus 4x squared plus 5 right here. Okay. All right, so on my computer, on my graphing screen, again, with the numerical labels are still completely hidden right here. This curve right here is my graph. It's the graph for that function I wrote on the board, x to the 4th plus 4x squared plus 5. Yeah, that's the function. And so this graph right here, unlike the earlier graph. Now, with the earlier graph that I brought in, okay, the earlier graph, we had some horizontal intercepts. We got 2 horizontal intercepts for the earlier graph. This is the graph for the x cubed minus 7x squared plus 15x minus 9. And then the graph for, and now I'm going to hide this graph away, and then the graph for the x to the 4th plus 4x squared plus 5 is now currently seen. So this graph here is another graph of another polynomial. However, this time, unlike the earlier graph, this graph does not have any horizontal intercepts, because the graph is showing itself right there, and in the way how you have understood up to this point, being an even power, being an even degree here, this graph is going to completely on the two ends behavior is going to completely go one way, and in this way how it looks, it's going to completely going up. So the lowest point on this graph currently is already that low point right here, that vertex right here. So it will never hit down to cross with the horizontal axis. So my point now is that this function, once we graphed it, okay, it will not, this function once graphed, it will not have any horizontal axis. So some polynomial, at this point we start drawing out some conclusion. Some polynomials have some horizontal intercepts, some other polynomial doesn't, okay? And then for this graph still, the x to the fourth plus 4x squared plus 5, this graph still has that vertical intercept right here. And let me bring that into a closer zoom right here, complete full screen view right here. So this graph, the x to the fourth plus 4x squared plus 5 still has that vertical intercept because it crosses through that vertical axis here. All right, so now before our journey starts right here, let's draw out the following conclusion, the following remarks, the following observation that will be true throughout any of our steps later on, okay? So drawing from that experience. So now this is what I'm writing it down right here, and we can start taking this as remark, or like I said, as an observation, and take note on this. So any polynomial will, okay, have exactly one, okay, or let me write it in number. We have exactly one vertical intercept, okay, in the way how we have observed two graphs so far, okay, and that will be the truth. That will be true. So to allow me to, to not formally proving it, but I will point out the reason why I can guarantee this. But any polynomial will have, for sure, it's a guaranteed result. Any polynomial will have exactly one vertical intercept, okay. And so I'm not completing my sentence here. Let's observe again a little more. Right here with our two polynomials, it's enough to tell the story, okay. So once again, let me bring the graph back. This is currently the graph for x to the fourth plus 4x squared plus 5, okay. And look right here at this intercept. Now I'm going to use the tracing feature right here with my decimals to hopefully land a point right there. So see, that point just now popped out is the point where you see right here, whatever this value is, it's not important, but this is the point where this is the point where the graph crosses with the y-axis. But crossing the y-axis means the x value must be equal to 0. Okay, x value must be equal to 0. Okay, and so in that same way, now I'm going to put the other function. This is the graph for x cubed minus 7x squared plus 15x minus 9. Okay, and so in a further zoom, I spotted a vertical intercept down here, okay. And again, it seems like it's the similar nature. I don't mean to bring out a precise value, but now at least one thing we know: vertical intercept happens at x equals 0, because just like the earlier quadratic function I brought up right there, this graph here is the graph of a cubic. It also crosses through the y-axis, the vertical axis, at the value x equals 0. All right. So now in that way, allow me to add into my sentence here. Any polynomial will have exactly one vertical intercept. Another way of saying any polynomial will cross the vertical intercept, the vertical axis, okay? And this is particularly now at x equals 0. At x equals 0, because that's the way how we find the vertical intercept. Okay, so anytime we let x equals 0, okay, that's y value comes out, that's going to be the vertical intercept. All right, and so in that way, we will apply this understanding into doing some more examples. But let me now bring up another observation from the two graphs we have seen so far that we can start generalizing some case right here. But now, so that was everything I can ensure you about the vertical intercept, okay? And we will come back and dive into more details that we can break down from this. But now, what about the horizontal intercept? Because so far I've only talked about vertical intercept. So now I'm saying a polynomial, a given polynomial, or a polynomial you're working with. So a polynomial, this is a little dangerous here, may, okay, or may not, okay, may or may not have a horizontal intercept. May or may not have a horizontal intercept. Okay, may or may not. And now, and then allow me to end that sentence there. May or may not. It seems a little dangerous, but we saw it right through the two cases, like that. Okay, so now let me bring back the graph. This currently is the graph for that x cubed that I had on the board earlier. So this particular graph here has two horizontal intercepts, okay? Whereas the graph for the quadratic that I brought up on the board did not have any. All right, and that's why, as I said earlier, any polynomial or a polynomial that we're working with may or may not have a horizontal intercept. Okay, so there's some case it has intercept and it may have even more than one intercept. But then at some other case, some other polynomial, it may not have any horizontal intercept at all. All right, so now from this understanding, we're going to start getting into finding it. Okay, and now let me talk even a little more about the horizontal intercept here. You see, and we will dive further into that. But on my graph, allow me to hide this x to the fourth plus 4x squared plus 5 graph away. And I'm going to bring back the graph for this cubic right here. Okay, so we call these points the x, the horizontal intercepts, in a sense that, see, let's look right at where they are right there. And right now, allow me to hide away the x values. But what I know so far is, at this point, whatever the x values here, y value must equal 0. Y value must equal 0. And the same with this one. Whatever the x values here on the x-axis, whatever the horizontal value will come out to be, that's what we will learn some techniques to find out. But now y value must be equal 0 in this case. Okay, and so let's draw out another general understanding regarding horizontal intercept. So now I'm going to say, so now no doubt about it. A polynomial may or may not have a horizontal intercept. But now if it had, right? I'm going to say at a, or how about let me continue this observation on the other board. At a horizontal intercept, okay, or at any horizontal intercept, the y value has to be equal to 0. Y value has to be equal to 0. That's why, see right here in this picture as well, mine. And it's not only just in the world of polynomial, okay? It's the general understanding about horizontal intercept, okay? And maybe even a little more precisely speaking, maybe for people who just came out from an elementary algebra course or any kind of prerequisite course prior to pre-calculus, we specifically refer to horizontal intercept as the x-intercept. If in any of those earlier courses of yours stay with the convention only that x is on the horizontal side and y is on the vertical side. So when we were learning the simpler math right there, then we stay with the tradition that x variable on the horizontal axis and y variable is on on the vertical axis. But now, and that's why back then we call that the x-intercept and the y-intercept. But now to equip ourselves for some more general situations, then we're gonna generally regard the x-intercept is one of those what we call the horizontal intercepts, because we may use a t variable on the horizontal intercept. We may use a w variable on the horizontal intercept. And the same with this on the vertical intercepts. Yes, traditionally we use y. That's why we used to call that the y-intercept. But now more precisely we call that the vertical intercept. And so now at the horizontal intercept, and I'm still staying with that tradition right here. So the y value or the vertical coordinates equals 0. That's what it is. Okay. Whereas just like that on your vertical intercepts, then the x value, see, so this is really, it's intended to mean that to enforce that the horizontal coordinates has to equal 0, whereas on the horizontal intercept the vertical coordinates has to equal 0. Just like that, y value is the vertical coordinates has to equal 0. All right, so on something like this, it's going to be whatever, if we call this the x, it's going to be whatever x comma 0. Whereas right here, that point, it has to be 0 for the horizontal coordinates and whatever the vertical coordinates that can be. All right, so it's some generality about a horizontal intercept and vertical intercept. And now I also add in the two general understanding that now specifically for polynomial, any polynomial will have exactly one vertical intercept. Okay. Because we can always place x equals 0 into our equation, into our function, and we will get to that through a couple of examples. But now a polynomial that you're working with may or may not have a horizontal intercept, okay? And so we're going to learn how to identify those. All right, so now I am going to erase my board here. Now again, I am looking at that function f of x equals x cubed minus 7x squared plus 15x minus 9. And there's another nature about these. So we've seen in the graph earlier that this function here, this polynomial here, has two horizontal intercepts. Okay, so now let me point out another nature about this, and then we're going to start looking at some solid techniques right here. Now with the graph of our polynomial f of x equals x cubed minus 7x squared plus 15x minus 9. Let's now find, because we know for sure it will always have exactly one vertical coordinate, vertical intercept. So let's, and we know one solid technique to get that. The vertical coordinates, the vertical intercept is always at x equals 0. Now, so I'm saying x equals 0 simply because our function was using x as the input. So now when the input equals 0, we're going to easily find the vertical intercept. Okay, so now back on the graph, I'm going to put in that point right there. All right, that point just now popped out. And allow me to change that to the black color right here. So this point is at coordinates 0, 9. 0, negative 9. Okay, and so 0, negative 9. So this is our y-intercept right here. This is our vertical intercept of this graph. All right, so that indeed brought up for us a solid technique right here to find. So right from here, if we are able to find the vertical intercept. So for on this particular, once we apply that on this particular function right here, the vertical intercept is going to happen at, we're going to purposely let x, okay, we're going to let x equal 0. So along the way, as I'm introducing, I am also introducing the technique to find the vertical intercept, okay, and it's the easier one, so allow me to introduce the easier one first, because and like I said earlier, any polynomial will have one unique and exactly one vertical intercept, and we only find that at x equals 0. That's why I'm going to start out purposely let x. I'm going to start out by purposely letting x equal 0. Okay? And now letting x equal 0, we substitute that in here. So now we're going to calculate y value at f, or as f of 0. Okay? And now I want to show you, as a calculation, how this result can be consistent with what we've seen on the graph earlier. The graph was showing 0, negative 9, and now we want to convince ourselves with the calculation. Because who knows, if we read the graph wrong. Reading the graph is a good tool, but it's only an estimate. It's permanently an estimate. So we need to get a precise calculation to verify our work. Okay, so like I said, now for vertical intercepts, only one solid technique. We're going to let x equal 0. Substitute that into the polynomial. All right, so now we're looking at the rule says cube the input, okay, where the input currently equals 0, minus 7 times the square of the input, plus 15 times the input, minus 9. All right, so now with these simple operations, which only involves raising powers, multiplication, adding, addition, and subtraction, with those simple calculation operations, then we know that for sure we end up with a negative 9. We end up with a negative 9. So the vertical intercept now is at, okay, at 0, negative 9. All right, that point right there is the vertical intercept, and that is now making it clear and consistent with that result we have seen on the graph. And this is what was on the graph here, 0, negative 9. All right. So now just for that, once we have concluded and that's really everything we need to know about the vertical intercept. So let's quickly push that into one short example, but it's one of the formal example here. Okay, so let's call that example 6 as a continuation from our earlier examples. Let's just say we want to find the vertical, okay, the vertical intercept. And so any polynomial will only have exactly one vertical intercept, so I will never write these terms in plural, singular only. Okay, so find the vertical intercept. So now and now how about part A right here? Allow me to really get into it. How about f of x equals, now that x to the 4th plus 4, x squared plus 5. I accidentally revealed the answer earlier when I was showing on the graph. Okay, but we can verify that. Okay, so the vertical intercept here, once again, to find out, we're going to let x equals 0, always. And we know for sure, even before we see the graph, we know for sure the polynomial will have exactly one vertical intercept. Okay, and it's only going to happen when x equals 0. All right, so that gives us naturally one solid technique right here. So now that y value there on the y-axis, on the vertical axis, and here because I'm using x to be my input here, so I'm using y to be my vertical output. Okay, so f at 0 equals, now the rule of this function says we raise the input to the 4th power plus 4 times the input square plus 5. So now input raised to the 4th power, add with 4 times the square of the input, okay, and plus 5. And so again, with only simple operations involved here, namely powers, multiplications, and additions, our final answer comes out easily 5. All right, and so now we're looking at the vertical intercept. Okay, so now as a conclusion, vertical intercept. Okay, 0 for x, 5. Okay, and that's in a pair of value. Okay, and that's our answer. All right, so that's how we're doing it. Let's try another one for here, and then we're going to also start drawing some conclusion right here. So I'm going to put in part B, and even at this part A right here, we already have done about 2 problems about finding vertical intercept if we include that earlier demonstration problem I've done with the cubic. Okay, so now let me bring up another one. All right, so for part B, how about I'm going to let f of x equals, this is x to the 7 plus 5x to the 4th plus 5x to the 4th minus 3x plus 1. Okay, some high degree polynomial, 4 terms. Okay, let's find the y-intercept or the vertical intercept. So we're going to purposely start out by letting x equal 0. Letting x equal 0, that's now we're going to proceed into calculating the y value. So once x equals 0, y value comes out as f of 0. Okay, so now the rule of the function says we're going to raise the inputs to the power 7 plus 5 times the 4th power of that input minus 3 times the input and plus 1. Okay, and once again, with only simple operations involved here, we easily come out with the final answer here for the y value being positive 1. Okay, positive 1. All right, and so now, once again, as an answer right here, vertical intercept. All right, vertical intercept is at 0 for x, comma 1. All right, so 2 problems in this example, including 1 demonstration problem earlier. We're starting to recognize a solid pattern, a solid way to easily recognize it. I mean, we don't even have to tear down this work right here all the times. This is the formal work, but then you also start getting into a quick way to determine, a fast way to determine, and it works anywhere, the fast way to determine vertical intercept on any polynomial. I underline it, only whatever the fast way I'm about to show here, it's only on the polynomial. It does not necessarily have to be for other kinds of function. Okay, but now before I'm revealing that, before I reveal that that truth right there, let's put in an FYT. Okay, so for anyone viewing the lesson here, to try on your own, how about let's look at a polynomial p of x equals, all right, negative 1/2 x to the 10th. I'm trying to go with as crazy power as we can, okay, plus, and then 7x to the 5th minus 3x squared plus, or how about here, I'm going to subtract 10. Crazy coefficients, having fractions and negative signs and, you know, high power, high degree. It's an FYT for anyone to try. Okay, I won't be showing much reasoning because, again, this is an FYT, but you can take similar work and the steps that have been shown in the earlier parts of the problem. Go ahead and get it done right here. Pause the video if you have to. All right. Okay, so now once you resume the video, this is your vertical intercept right here. So now without the need to show the reasoning, I'm just going to tell the final answer here. Vertical intercept here is simply just at 0 for x, as you already see that often enough, and now minus 10 for y. Okay, and this is the answer. So 4 problems done, 2 problems I led the way, 1 problem I demonstrated the idea even before that. Okay, and now 1 problem I left it all for viewers to give it a try, or students who learn in this lesson to give it a try on your own right there. Now that general conclusion, we can use this valuable little observation right here. Okay. The constant term in any polynomial is the y-intercept, or just more formally the horizontal intercept. All right. So we don't even have to formally substitute 0 in, because whatever observation here I've made, it came out from plugging in x equals 0, the input value equals 0 into the polynomial, and look at what we came out. We came out with precisely that constant term. Okay, this was your FYT problem. Okay, the earlier one I've made, the x cubed minus 7x squared plus 15x minus 9. That's a final constant term right there. This was our y-intercept. And of course, writing that in complete points, and it was 0, -9. All right, and then that earlier one, in part of this example here, x to the 4th plus 4, x squared plus 5, this last one right there was our y-intercept, okay? That was our y-intercept. The computer was reading that as 0, 5, okay? All right, and then the one we just did here in an FYT, and the one I also did, which I already forgot what that was. Okay, so that's how we find the vertical intercept. There's no need to keep going further into the details, because that's all the details there is, and that's how simple it is to find vertical intercept. All right. And so now let's head our way out to horizontal intercepts, and this is where it's going to have a limitless amount of details here, and it's such a fascinating world for the mathematicians to study right there. So let's now look into the horizontal intercepts. All right, and now specifically horizontal intercepts of any polynomial. So nail this down that I've said earlier, and now here I'm saying horizontal intercepts because it may have an intercept, it may not have an intercept at all, or it may, and once it have an intercept, it may even have more than one intercept. That's why now I'm saying, and I should have put that in parentheses, it's for optional plural over here, but we may have more than one horizontal intercept as well. Okay, so let's get to it. All right, so again, allow me to bring up the two little functions that I brought up as demonstrations. Okay, so how about one of them was the f of x equals x cubed minus 7x squared plus 15x minus 9. Okay. And this other function I brought up, and we can also say with the same name, f of x equals x to the 4th plus 4x squared plus 5 right here. Okay. We saw that this one had no intercept, because the graph told us, the graph mentioned that, the graph displayed that, okay, no intercept on this one. Okay, so let's cross this out of our attention. I'm not saying that I'm not saying that we're never gonna work with this function again. Okay, well, I mean we just learned that those general technique to decide or anything. But for now, since we already knew this function here, this polynomial here has no intercept, no horizontal intercept to be precise. Okay, no horizontal intercept. Then let's not pay attention to it. Let's pay attention to this one right here, where the graph showed it had two horizontal intercepts. Okay. All right, so let's now look at the graph for this particular one, x cubed minus 7x squared plus 15x minus 9 right here. All right, so here we go on our graph. Now this was that y-intercept, the vertical intercept. We don't need that there any longer. I'm going to put it away. Okay, so now I am going to actually put in the grids. I've been hiding the grids away throughout all that time, but now I'm going to put the grids back. Okay, so this is the grid. All right, and I'm going to put the axis numbers. Okay, the numbers on the axis. Now the answer all of a sudden becomes a little more clear. So it looks like in a way how we're currently observing the graph right now, it looks like the graph crosses through our horizontal axis at one point. That first point, and of course from the left to the right, from the left to the right. So the first point here is at x equals 1. Okay, And the next point here, according to my observation, according to what I see through my own eyes right here, it's x equals 3. Okay, so let's just quickly experiment it. That's all I'm saying. Let's just experiment it. Okay, so now I am going to erase this page of the board. All right, so let's just experiment it. And now, this is how I see it. Well, we saw on the graph earlier, so all I'm saying is whatever we saw from the graph was just an estimate. So it seemed, right, that x equals 1, right? I'm just documenting the observation was a horizontal intercept. Okay, it seems like that. So how do we verify? So now I'm just talking about verifying what we saw earlier, verify what we estimated through the graph. Okay, so remember what I said also earlier, when it's the horizontal intercepts, the y value have to equal 0. So that suggests a perfect direction for verifying. So all I said in that abstract where it seemed that x equals 1 was a horizontal intercept. I said this because that's what we saw once we put the grids back on the graph. And now we need to verify. So the only way to verify, I'm going to substitute this into the function, into the polynomial. So now let's calculate the y value. And so now as a goal, we want y value. Okay, as the goal, we want y value equals 0. That's what we want in order to verify that, hey, x equals 1 on the x-axis, on the horizontal axis, really is our horizontal intercept. Okay, so now I'm doing y value equal f of 1. And f of 1 means, and 1 is the input, needless to say. So 1 cubed minus 7 times 1 squared plus 15 times 1 and minus 9. All right. You can pause the video and perform your own calculation on this. Okay, but anyone viewing this video, allow me to assume that you're mature enough to allow me skipping the calculation step here. So really calculating this out, I do end up with 0 for y value. Okay, 1 cubed is 1 minus 7 here plus 15 minus 9. All right, so minus 7 minus 9 and plus 1 and plus 15 right there. It's all going to 0 out. All right, and so now that means yes. So as far as the horizontal intercept, let's just conclude that out as a list right here. Horizontal intercept, okay? Then yes, x equals 1 was one of them. It's earlier, in my logic, so far earlier, right after observing the graph, it seems that x equals 1 was one of them. We verified it. Now we put it formally into our list. Horizontal intercept, x equals 1. Okay? And so now, let's look back on the graph again. This same graph right here, so apparently this polynomial has at least one horizontal intercept. Okay, unlike the case of that quadratic that I wrote down, and then we had to disregard it because that quadratic there did not have any horizontal intercept. This one does have, and as a matter of fact, even more than one intercept. So let's look at the other one. So now on my graph here, it looks like we have another one. This is where the graph hits with the x-axis, okay? Hits the x-axis, and it seems like it hits down to x equals 3. And that's why all I can say it seems like, okay? Because we never know for sure, because it's just the way how the resolution of any graph, no matter how close I zoom in, we're still not sure if it's really at x equals 3 or somewhere x equals 0.001, 3.001 or something like that. And that's the reason why now, taking account of that point, I'm not going to put it on the board, and I'm going to repeat that logic again. It seems that aside from x equals 1 that we already verified, it seems that x equals 3, okay, was another, how about, let me was another horizontal intercept. Okay, and so now I'm going to repeat that logic right here. The goal is when it comes to a horizontal intercept, the y value, the vertical value needs to be 0 there. Okay, that's why the goal here is y has to equal to 0. And so now in that way, how do I verify? How do I verify that this really is? Instead of saying it seems that x equals 3 was another horizontal intercept. So now we want to get it solid, clear, crystal clear. So now y value equals f of 3. We're substituting x equals 3, the value that it seems like. Okay, we substitute that into the polynomial. So now x equals 3. When x equals 3, our function turns out, according to this rule right here, 3 cubed, which makes 27, minus 7 times 3 squares, okay, plus 15 times 3 minus 9. And I'm still holding on to this list right here. If this calculation turns out another 0, then I can say x, I'm going to go ahead and put x equals 3 into my list, all right, of the horizontal intercept. But now, once again, I want you to pause the video and verify on your own with the calculation here, because anyone viewing this lesson should be mature enough in your calculation skill right there. Okay, and the answer here should be this, the calculation should come out 0. All right, so now, because that's 27, and all of that here, that's minus 56, okay, plus 45 and minus 9 like that. All right, so it's all going to 0 out. Because that's 27, and minus here, this is 63, plus a 45, okay, and minus 9. And that should come out all equal to 0. All right, and so now we have verified another one that, hey, x equals 3 is also another the horizontal intercept. So now, and let's look back at the graph one more time. And now with the graph right here, okay, with the graph right here, it doesn't look like there are any other, it doesn't look like there will be any other intercepts. And we will get to that details where we can verify there will be no more intercepts beyond these two right here that we have found. All right, so now I have now I can say that I have found for this polynomial right here, there were 2 horizontal intercepts, x equals 1 and x equals 3 right here. We found 2. All right, so now before I'm leaving this demonstration problem, this demonstrating the polynomial, I have to highlight the following. The form I initially gave it, here was recall from your previous learning, just from the earlier part of this lesson. This is called a general form, okay? The general form. And so once it's given in a general form, it seems a little hard. So without seeing the graph, with our graphing utility, it seems a little bit clueless. Right now, at this point, it seems a little clueless about how we can find, and that's why we need to eventually learn some technique right here. Okay, but here I just want to emphasize that this demonstration problem, this demonstrating the polynomial is given in general form. Okay, so now I'm going to get to the other board and allow me to bring in the following. All right, so how about, let me introduce x minus 1 times x minus 3 all square. X minus 1 times x minus 3 all square. Okay, so do a little verification for yourself. Do foiling, foil out this, because this is x minus 3 times x minus 3. So really this is, I mean, right now as first sight, it's a polynomial in factor form. This is in factor form. Okay. And now you can verify that this really is that x cubed minus 7x squared plus 15x minus 9. Now I want you to verify that by foiling this factor to get into that the general form. But this right here I've just written down, it's the factor form of our exact same polynomial. So here's the advantage, and this is the reason why earlier in the lecture I was spending a decent amount of time to make you comfortable with the factor form of a polynomial, and I really try my best to enforce the understanding that a lot of times, many times, a polynomial can be given in a factor form. And this is now some good advantage of having a polynomial already in factor form. It's just some good advantage that comes along. Okay? Didn't we just agree earlier from the other board? Didn't we agree earlier that x equals 1 was one of the horizontal intercepts? Now we found this through the graph, and we verify this through the mathematical work right here. Okay, so but that's, I don't want to close down the case right there that we're studying, and I want to keep seeing more details. So we already agreed that x equals 1 was a 1 among the horizontal intercepts. We had 2 horizontal intercepts for this particular function right here. So now in that understanding, in that previous understanding we already had, see, intercept, horizontal intercept. To save myself from keep walking back and forth right here between the two boards, I'm going to write it down. X equals 1, and we had another one, x equals 3. We have 2 of them. Okay, so now x equals 1. Look right at that factor right there. Look right at that factor. Look right at that factor. It has something that explains. All right, so now as a matter of fact, you see x minus 1 right here. Just think about if we set that x minus 1 equals 0. Okay, because, and for now x minus 1 equals, x minus 1 being equal to 0, we solve x minus 1 itself is a linear factor of this polynomial. Okay, and so now I will explain a little later why we set that equal to 0, but see, think about if we solve x minus 1 equals 0 for x, then adding 1 from both sides, we end up with x equals 1, and this is consistent with one of our horizontal intercepts. And so think about the other one. This x minus 3 right here must be related to that factor, but this factor, be cautious a little bit. It's the x square, it's the square form. It means x minus 3 times x minus 3. But now just think about it. If we simply take that x minus 3 and set it equal to 0, x minus 3 itself and set equal to 0, then we can just simply add, and this is just usual stuff from our previous course right here. It's very simple linear equation, set it equal to 0, okay, and then we solve that for x value, x equals 3. And so we come back to that value among the horizontal intercepts. So what is that point I'm trying to make here? All right. All of a sudden, why am I leading one of you into this? Because I'm on my way to show that solid technique right here. Okay, so far it's just observation. So observations show that observations I've been making is showing that one important fact. If, I'm obviously saying if we can successfully put a polynomial, maybe started out in general form, but if we can put that in a factor form, then we can have the following advantage. Okay, and look at what I'm trying to show right here as a demonstration problem. So now we know that the x cubed minus 7x squared plus 15x minus 9 is equal to the x minus 1 in product with x minus 3 squared. So this is our same polynomial, f of x. Okay. Finding horizontal intercept. Okay. Finding horizontal intercepts, there could be multiple, but at the very start, we're gonna let y equals 0. All right. Recall from earlier that when I was saying if we have any horizontal intercept, the vertical coordinates there has to be equal to 0. It's the way it is for any graph. It's the way it is for any graph, not only just the polynomial, anytime our graph is crossing with the x-axis, with the horizontal axis, the y value, the vertical value have to equal 0. So now in the work of finding any horizontal intercepts, we need to let y equal 0. Okay, and so letting y equal 0, and so I'm slowly getting you into that solid technique right here, letting y equal 0. And if we knew our polynomial has a successful factor form that was previously addressed here, then that leads to y equals 0 will lead to this factor form x minus 1 times x minus 3r squared equals 0. Now we have an equation to solve where our left-hand side, now one side is completely 0 and the other side is completely in factor form. So now we have learned this from our previous course. If we can put our equation in this form right here where, this one side is 0, the other side is completely in factor form, then in that way we can, and this is why I was able to do that earlier work I show on the board. This is why now, as long as we can reach a factor product on the opposite side of 0, then we can start extracting out, we can start separating out, as we're going to let each one of those a unique factor, See, so x minus 1 is one of the unique factor. I'm gonna be able to set that equal to 0. All right, and I'm also gonna be able to separate out the other unique factor, x minus 3. Even though it had the square, but that square or that cubic or that whatever power here is just simply how many times. Remember I used the term multiplicity earlier in the lecture. So that's just simply how many times the factors appeared in the whole product. Okay, but in the end, doesn't matter how many times that factor appears, then if we treat them all as unique factors, then in the end all we need is just the x minus 3 equals 0. And that's why I have produced two separate little equations to solve for, and then continuing to solve each of these. That's why adding 1 from both sides, I ended up with x equals 1. That now comes back with, that's now what explains for how we have that the horizontal intercept here to be one of them is x equals 1. The other one came out from adding 3 from both sides of this small little equation, okay, and that land us into x equals 3 right there, and that's what explained for this other value right there. Okay, so we investigated and we already knew by heart that these two were the intercepts, but now I'm trying to explain this is now becoming, all of a sudden it's becoming our technique right here to actually solve for the horizontal intercepts. Okay, for horizontal intercepts, if we have if we can successfully, the dangerous line here is if we can successfully put our polynomial here into the factor product, then we can go ahead and use that property of an equation. Anytime we have a product on the left, on the opposite side of 0 equals 0, then we can break apart each of the unique factor here and set it equal to 0. And now, depending on how many unique factors we have, we're going to produce that many x values satisfying the equation equals 0. All right, and that's consequently become our horizontal intercepts. All right, so in that way, now that famously introduces the factoring method to find a horizontal intercept. Keep in mind one thing. I am not saying that we can always, and remember I said earlier, if we can be successful in terms of putting this polynomial into a factoring product, I'm not saying that factoring product is always easy to find. I'm not saying that, but let's get started into some examples where I'm going to give some polynomial where it's easy to do the factoring product so that we can find horizontal intercepts. Okay. All right, so let's now look at our example 7. Okay, so this example here, I am going to say I want to precisely find just focus on the horizontal intercept. Okay, so let's find the horizontal intercept. Okay, and there may be more than one intercept. So I'm just saying that S right there. Okay, find the horizontal intercept. And so the point here is that we don't want to use the graph. We want to use the solid factoring technique right there. Okay. So how about algebraically? So, all right. Find the horizontal intercept algebraically. Okay. So now let me introduce part A. Okay. So part A of this example, my function here, my polynomial here is x minus 4. You will be shocked that I gave such an easy problem right there. But I want to build your skill again in case your past understanding has faded away. I purposely brought this in a pre-calculus course so that you will build your experience up again in case that the learning from your past courses has somehow faded away. Okay? It's a polynomial, no doubt about that. But this is the easy case. It's a linear over here. That's what I recognize. Okay? This is linear. It's already linear. Okay? And so now, when we find a horizontal intercept, yes, that fundamental we have seen earlier, we need to let y equal 0. Okay? So now to find a horizontal intercept, we have to start out by letting y equal 0. And so now y equals 0 means, well, and y is supposedly equal to our function x minus 4. And again, it's linear, only two terms. This is a constant term. That's the first power term. And so now, purposely letting y equal 0, we're producing x minus 4 equals 0. Now, anyone viewing this lesson will be convinced that this is an easy problem. You have seen this all over of your prerequisite courses. Okay? What we do here is simply add 4 to both sides of your equation. And we will produce x equals 4. Assuming our math went fluently and without any errors, and this is our final answer right here. Okay? And we can double check. We can double check. Maybe it's also a good idea to double check. How do I double check? We did the math work. We found the value here. So this is tentatively our horizontal intercept, or a little more friendly, the x-intercept. Okay? This is friendly, the x-intercept. But now, how do I check if I did that without any error? Okay? Then here's how I'm doing it. Remember, we want y equals 0. We want y equals 0. So in that way, f of 4. Just put that into the function itself. Put the value we found into the function. And we want to verify that this value we found will ensure y equals 0. All right, so f of 4 equals, the rule of the function says 4 minus 4. And that is equal to 0. So that now verified that this is our correct solution. We have found our horizontal intercept here for this particular function. All right, so let me now look at another one. All right, so part B, and allow me to still purposely, I try to blend some of your, some review for you. Whoever learned from this lesson, some of the review from your past material, and blend that in to be as part of the understanding for this pre-calculus course right here. So how about another function here? How about p of x as a polynomial? How about now I'm going to have a 5x minus 2. It's a linear function again. It's a linear function again. So it looks like right now the professor here is still focusing on the linear one. I want you to be fluent. Your whole family of polynomial is built on a lot of skills from the linear function. So never look down on a linear function. Even though you may feel you are already way past the linear functions, you have seen that 2 or 3 courses ago. That's not the point. We continuously have to be fluent with linear function. Okay? It's a polynomial. See, a completely new view about that. So now with this polynomial, let's look for the horizontal intercept. All right. And so now at this point, I'm going to purposely let y equals 0. All right, letting y equal 0 in this case means, that's why I'm using this arrow, it's letting y equal 0 leads to producing 5x minus 2 equals 0. Consequently, okay, and then by doing this, now all of a sudden we realize, hey, we are finding the x values, making the left-hand side equal the right-hand side. Okay, so in that way, the method that you have seen in your previous courses now counts. Okay, I'm going to add 2 from both sides. All right, and so that gives me 5x equals 2. I'm going to divide both sides of the equation by 2. I mean by 5. Okay, and so now I'm ending up with my final value here. X equals a 2/5. It's fraction, but it's okay. It is now a horizontal intercept. Okay, it is now a horizontal intercept. Okay, but so now once again, so tentatively, this is our horizontal intercept. If we did the calculation correctly in every steps here, and you can already see that I made some little mistakes when I was writing it, and I had to erase it and all that. Okay, so in the case where you want to double check, again, how do we double check? We just want to substitute this back into our function f of 2/5. The goal here is we want to, the whole point of finding this value x right here is we want to find the x value satisfying f of x equals 0. So we want to do f of 2/5 here to equal 0. We want that to happen. So let's find out. 5 times 2/5. The rule of the function says 5 times the input minus 2. 5 times the input, which is now 2/5, minus 2. 5 cancel with 5, so that consequently ending out with 2 minus 2. That gives me a 0. So now we knew that we've found our solution correctly. All right, and so now, 2 problems so far, okay? 2 problems so far. As long as being a linear, it's a polynomial. A linear is a well-deserved, linear function well-deserved its place to be in a polynomial family. Okay, so being a linear function, what have we drawn as a conclusion so far? Linear function, any linear function, we have a solid technique to solve for equal to 0, okay, and we've learned that technique back in those courses long ago. That's why here we kind of doing it as a polynomial, and you reviewing your skills like that from the past course. But now that general conclusion I would like to make here is that at the end of the example 7 here is that we can take this as a remark, okay, and you may want to treat that as a red remark because it's important enough to notice, okay, but any linear polynomial, okay, it's a polynomial but first degree, so any linear polynomial will have, so this is sort of like a guarantee, will have exactly one horizontal, okay, one horizontal intercept. All right, that's one thing we drew out as, so this will also give us, so now in our newly built experiments, newly built experience, okay, then now this is a way to guarantee. So a lot of times you're in a situation where you don't even have time to sit down and formally find, because earlier I was showing you the work to find the horizontal intercepts, but there will be times where you don't really have that valuable time to sit down and show your steps to find the horizontal intercepts. But you can still quickly look at the function itself and be able to determine whether it will have an intercept, a horizontal intercept, or not. And so now specifically I just start putting into your attention, your awareness that, hey, anytime it's a linear polynomial, it will for sure, it's guaranteed to have exactly one horizontal intercept. Okay, it's a remark. So if you want to put it in your memory, or if you don't want to, that's completely on your choice there. But if you remember this, it's gonna help significantly in many of the problems later on. Okay, and so in that way, now before I completely leave the example 7 right here, then let me put in an FYT for anyone to try. Okay, so alright, so as an FYT, let's look at a polynomial being q of x, and how about this time it's a minus 4x plus 1. Alright, so go ahead and pause the video, spend your time finding that horizontal intercept right there. Okay. Alright, so now as you have resumed the video, I assume you already have some answer and showed your steps right there. In this problem, it's an FYT, so I'm not going to show the steps anymore. I will just show the final answer. So that horizontal intercept is x equal negative 1/4, okay, as a fraction. Alright, so now it goes a little loosely when it comes to intercepts in general. Okay, vertical intercept or horizontal intercept, it goes a little loosely. That sometimes in a rush situation, you are allowed to leave your answer in the only one single value like this, because of course the other value has to be 0. So needless to mention, and so we only need to indicate when it's a horizontal intercept, we only need to indicate the horizontal value right here, even though ideally indicating both would be better. Okay, so like in the case of the vertical intercept I did earlier, then I was formally putting that in a whole pair of values, the x value, I mean 0 for x, and y value on the y-intercept. But here, when things starting to get a lot more details, and it's completely okay to just skip the y value, because here when it's horizontal intercepts, y value, needless to say, it's 0 already. Okay, so it's more anyone is going to be more interested in seeing the x value that causes the y value equals 0. Okay, so it's okay that you only write one value like this instead of a whole complete pair, like how I was indicating the vertical intercept earlier. Okay. So now, at least throughout the example 7 here, we have seen some solid technique, and that hopefully reveals your skill, how you solve the equation, a linear equation in general. Okay, but then we apply that skill into now the work we call is finding the horizontal intercept of a polynomial. And here specifically in example 7, all of those problems in our example 7, here is a polynomial in degree 1. A polynomial in degree 1. Okay, so now let's continue into another example. And we're still finding horizontal intercepts or intercepts, okay? Let's now call that example 8 right here. Let's find a horizontal intercept algebraically. All right, so I'm going to call that now part A of the example. How about our polynomial here? F of x equals it's an x squared plus 6x plus 8. It's an x squared plus 6x plus 8. Okay, so now before we get started, now, again, here I intended to solve, my intention here is to find the horizontal intercept algebraically, but maybe it's a good idea to look at the graph before we get started. Okay, and you also know from your previous course that this is called a quadratic. In our current understanding, it's a polynomial, degree 2. But from past understanding, from previous course, we learned that this is called a quadratic equation. The a coefficient is 1 in front of the x squared term. The b coefficient is positive 6 in front of the x term, and the constant term is here. Okay, so let's find the horizontal intercepts. But like, as I said earlier, before we get to that, let's quickly look at the graph. Okay. All right, so now on my empty graphing space right here, this is the graph for x squared plus 6x plus 8. All right. So I will make a formal understanding about this, but just as a recall, we have a quadratic graph right here, the graph of a quadratic, and the picture here, the shape of this picture is called a parabola. Okay, and we already saw through the picture that we will have two horizontal asymptotes. And we already saw through the graph here that we will have two horizontal intercepts. But then we're not, the point now is that anytime we're looking at the graph, it's only estimating. So we want to use the algebraic technique to solve for this and to ensure that these are the whatever we observe here will be the correct one. So even though I have values placed, the numerical values placed on the line of numbers here, but I'm still not going to trust these values, even though we thought we found the horizontal intercepts. But let's do the work algebraically. Okay, we just know that it seems like the graph here crosses the horizontal intercept, the horizontal axis at two values, that's 2 points. That's all I need to enforce like that. So now I also brought in this example 8, and I also brought in this problem here as a brief review for any of you in case your skill in handling quadratic function has faded away. Okay, so again, to find algebraically, to find a horizontal intercept algebraically, the first thing we need to know, and it's a general understanding we picked up from earlier discussion, anytime we're finding horizontal intercept, we're gonna let y value equals 0, just like how we were doing that in example 7. We're going to let y equal 0. So letting y equal 0 will lead to producing for us the following, because y equals this whole quadratic function. A quadratic is now, in our understanding, a polynomial, degree 2. And so now I'm looking at x squared plus 6x plus 8 equals 0. Okay, x squared plus 6x plus 8 equals 0. All right, so now, ladies and gentlemen, what we realize here, I'm not saying that I start solving it yet. All I'm doing here is just putting in a setting up point right here, a starting out point right here. This form right here, yes, we famously know that as a quadratic equation. All right, a quadratic equation. Okay, so now quadratic equation, from your previous course, from your past understanding, there are 3 separate methods to solve right here. We can complete the square shape, and we call that quadratic equations. Ideally, we call that quadratic equation after we have put all non-zero terms to one side and leave completely a 0 on the opposite side. Once we have done doing that and recognize there's a square term in our equation on the opposite side of 0, and we call it a quadratic equation. Okay. Otherwise, when terms are still all over, on the left and on the right hand side, and we have to bring all terms to one side first before we can say it's a quadratic or non-quadratic. Okay. So now, clearly speaking, once all non-zero terms are being placed on one side and completely showing a square term right here, then we call this a quadratic. And now, talking specifically about solving a quadratic for x equals 0, for x, because we want the left-hand side equals 0. We want the polynomial equals 0. Solving that from your previous course. Now I can remind you, from your previous course, we have 3 separate methods to handle this. Now, I'm talking about 3 independent methods to solve algebraically. Okay, the graph is just a graphical solution. We're going to handle that later. But algebraically, I'm talking about methods, how to write it down, and the calculation, the actual precise calculation. Then one method is to complete the square. Option number 1, we can go with complete the square. Okay. So allow me not to show this method in this example. I will have separate video lessons, okay, to show this fundamental skills here. But it's not too relevant for our work here in this pre-calculus course, especially seeing it as a polynomial. So allow me, I only mentioned that you can use this if we are in that situation. You can use this Okay, but in this example, I am not going to go with that method. It's just a reminder that you have that method to solve. But how that is done, allow me to show that in a different video lesson right here, and not even a video lesson for this course. Outside from complete the square method, we also had another method called the quadratic formula. This quadratic formula works anywhere, but only work for the quadratic function. Only work for the quadratic equation. Okay, and so for that reason, also allow me not to use this method. Allow me not to use this method to solve this equation right here. Because yes, it works too. It will work, and it will always guarantee you will come up with the final answer. Okay, but it's not directly relevant to the fact that your quadratic is being a polynomial. Okay, so allow me to only keep that as a reminder that you can always use that as another option right there. Okay, allow me to point out this option right here where you will carry that experience from here to the later, the harder problems. The third method right here is the factoring method. Okay. All right, so this method here I'm about to show in this particular example is the factoring method. We also learned how to do this when anyone was learning about solving a quadratic equation. But this method is also a universal method that solves any higher polynomial for 0. And that is the reason why I want to dive into this one, even though it may be or it may not be a method that you favor. Okay, so factoring method. All right, so the factoring method. And so let me clarify before I get too far. So in what I said earlier, see, complete the square is a method well working, very well working, but it's only valid for quadratic equation. So you only use this when your equation that you're solving here is a quadratic. When it goes in, when you are particularly, remember our main goal here is to find horizontal intercepts. And now we learned that specifically for this problem it's a quadratic. That's why we have this complete the square or the quadratic formula. But these two methods are quadratic oriented, quadratic functions oriented. So it's only work when you're on a quadratic function, which consequently produces quadratic equations for you. All right, and the reason that I particularly chose to show in this example the factoring methods, because this is the method that's independent with whichever the polynomial you work. Any polynomial you may or you may not be able to factor. It's a challenging method, but it's a universal one. All right, and so we're gonna just learn, at the best we can. We're gonna learn just as the best we can. Okay, so the factoring method. So now, to blend in with your major understanding at this point right here, let's start out with the polynomial itself first. F of x is the x squared plus 6x plus 8. Okay, so being specifically looking at this as a quadratic, then we've learned that easy technique from your previous course. That, and by the way, this is leading coefficient 1. Leading coefficient 1. So now we're going to set up two pairs of parentheses. Okay, and when classes are face-to-face, I keep making this joke to my students that nothing is easier, now when it's come to quadratic as your polynomial, nothing is easier by producing two pairs of parentheses and put an x here and an x there at start. Nothing is easier than doing that. Okay, and by the way, that was because we have leading coefficient 1. So when it's leading coefficient 1, just boom, get straight into two pairs of parentheses with an x here and an x there. Nothing is easier than doing that. And now we're going to find this, anyone will know this. We're going to find two factors of 8. Two factors of 8 including sign. So 8 here, two factors of 8, it could be including signs. It could be a positive 4 and a positive 2. That's multiply. I'm talking about positive 4 and positive 2. That's multiply. Okay, or a positive 8 and a positive 1. But now I want two factors of 8 that's sum to this middle coefficient. I want two factors of 8 that sum to this middle coefficient. Okay, and my way of verbalizing this may not be the best way, but believe me, you have seen this method all over in your past experience. So if my way of explaining it verbally does not work out too well for you, you go with the method you've learned from your past teacher like that. But now I see plus 4 and plus 2, because now these are the two factors of 8, but they sum to positive 6. That's what I want. And now all of a sudden I realized this is my factor product. This is a factor product of the exact polynomial I started out in the beginning. Okay, this is a factor product. Okay, factor product or factor form, okay, of the polynomial. I want you to see, yes, admittedly it's a quadratic, but I want you to see in a more general understanding. It's a polynomial. It's a quadratic polynomial. And we just have just now, this is general form, this is factor form. Okay, and so now again, back to the work that I was doing here. It's all about we want to find, so finding the horizontal intercepts. Algebraically, we want to set the equation here equal to 0. Okay, we want to set the polynomial equal to 0. So now with the factoring method, and I show the factoring separately on the other board. So let's continue with that on this board right here. So now that means, so now back to our work. X squared plus 6x plus 8 equals 0. Now that leads to, in factor products, it leads to x plus 4 times x plus 2 equals 0. Because keep in mind, I show this work separate right here, but the point now is that if we were able to, or if we were successful to put our polynomial into a factor product, so similar to that demonstration example I've done even before we got into example 7, okay, then now I can simply, once we see we have two unique distinct factors here, then now I'm going to produce one separate equation. X plus 4, one of the unique factors to equal 0. I'm going to have another one, x plus 2, one of the unique factors, and the other unique factors. Okay, and now I'm going to continue solving each one of these separately. Okay, so now x equals -4 here, subtracting 2 on this other one, x equals -2. Now, ladies and gentlemen, these are our two horizontal intercepts. These are the two horizontal intercepts for this particular quadratic, but as a degree 2 polynomial. A degree 2 polynomial. We found this graph here, the graph of this will cross the x-axis at x equals -4 and x equals -2. Okay, let's look back at the result on the graph. All right, so now with the graph, now I can keep zooming it in, and it does show that it crosses right at x equals -4 and x equals -2. All right, and so the result we have just found, algebraically, okay, verified our work, but this is also a solid technique. So I showed the factoring methods, and the factoring method worked with a lot of quadratics. Okay, I'm not saying that it works on all. Factoring method doesn't always work, but it's the universal methods. Okay, so complete the square or quadratic formula only works on those polynomial being a quadratic, but now the factoring methods, if it works, okay, it works on any polynomial, okay, if we can make it work. But of course, I'm not saying that we can always find the factor successfully. Okay, and that's why there are PhDs out there who will study and who spend their entire lives to learn about factoring out a polynomial. Okay, it's all for serving this purpose right here. Okay, let's get back and do another problem right here. All right, so let's look at part B right here. Okay, so I'm going to call that the polynomial here. Again, let me show another quadratic right here. X squared minus 4x plus 4. Okay, x squared minus 4x plus 4. And so now to find the horizontal intercept algebraically, we first start letting out. We're starting out by letting y equal 0. All right, and then that will consequently produce for us the equation x squared minus 4x plus 4 equals 0. All right, and so now let's spend some time finding the factor form of this polynomial. Like I said, we're going to go with the factor method right there. So sort of like on the side work right here. All right, so x squared minus 4x plus 4. It's still good thing, it's still leading coefficient 1. So nothing is easier than producing two pairs of parentheses with an x here and an x there in the other pair of parentheses. And now once again, let's look for two factors of 4, including sign, two factors of the ending, two factors of that the constant term right there. Okay, let's look for two factors including signs that sum to the middle coefficient -4, sum to -4. So those must be -2 and -2, -2 and -2. All right, -2 and -2. And so in this case right here, that means now the equation here becomes x minus 2. But instead of writing x minus 2 times x minus 2 equals 0, which is right, x minus 2 all square. Okay, and now that equals 0. All right. And so now, in this way, really it's even though tentatively it's two separate factors, but tentatively it's two factors, but now the two factors are repeats of each other. All right, so in that way, now we only need to just set x equals 2 equals 0, one of those, because the other one will be the same. Okay, so x minus 2 equals 0, and then now we're going to solve that for 0, and that, so x equals 2 out from that. Okay, so now let's verify through the graph. So, all right, so on our graph here with the empty graphing space right here, this is the graph for x squared minus 4x plus 4. Okay, so unlike the earlier problem, this time it's a quadratic. The earlier quadratic had two solutions, had two horizontal intercepts. This quadratic here, just the same degree, but has only one intercept. Okay, and so that's why, like I said, even we have learned earlier, even some polynomial has no intercept, or may have some intercepts, or even more than one. All right, and so we will get also to formalize into all that idea. Right now we just learned the solid technique, and the technique here is to be able to put your polynomial into a factor product. And so the repeated work I've been doing so far is that once we have successfully put our polynomial into factor form right here, then we're going to just simply extract out or separate out each of those the particular linear factors, equate that with 0, and solve that for the value. And then sometimes the more than one, sometimes some factor is repeated, like in this case right here. And we will get through all of those details right there. All right. Let's now look at another example, another problem. All right, so f of x equals x squared minus x, okay, plus 1. X squared minus x plus 1. X squared minus x plus 1. Okay, so now we want to let y equals 0, and that consequently produce for us the equation x squared minus x plus 1 equals 0. Okay. And once again, that factoring method, I'm about to use it. Okay, I'm about to use that factoring method. But here's the thing. Now when we start attempting to find a factor, see, and this is like I said earlier, that it's not always easy to find a factor method, I mean a factor product of your polynomial. So here we're working specifically with quadratic, but keep this in mind, it's not always, and especially among the quadratic, it's already quite challenging sometimes, like say the case right here. Okay, like, so with that technique I've used so far throughout the two problems in this current example, find two numbers, find two factors of 1 including signs that sum to -1, find two factors. And like I said, well, good thing is the leading coefficient 1 here, so x here and x there, but the two factors of 1 including signs that sum to -1. Is that -1 and +1? That doesn't seem right, because these are not a factor of 1. They don't multiply to be +1. Okay, so that's has to be ruled out. Okay, how about +1 and +1? Okay, they multiply. They are factors of 1, but they don't add up. They don't sum up to be -1 here. Okay. What about -1 and -1? Okay, they multiply to be a 1 here, but they don't sum up to be a -1 here. They multiply to be +1. -1 times -1. They multiply to be +1, but they don't sum up to be -1 here. We're still stuck, quite stuck. Okay, and so now another truth, but this truth is within the quadratic right here. Now, this A coefficient is 1, the B coefficient is -1, and the C in your quadratic is 1. I'm just trying to bring it back to that familiar quadratic equation or quadratic functions experience right there. Then now do the following setting: b squared minus 4ac. This technique is only valid for quadratic, but it can tell me something. This calculation here gives me b squared minus 4ac. B squared is -1 minus 4 times a times c. It gives me a 1 minus 4, which is -3. It gives me a value being negative. This is a perfect sign telling me that on paper and pencil, without looking at the graph, this is a sign telling me that this quadratic will not have factor form. Do this, b squared minus 4ac. Anytime you're looking at a quadratic polynomial, anytime you're given a quadratic polynomial and attempting your way to find factor product, factor form of that, do this first. Do this first. So I should have done this back in the earlier problems right there. Okay, but I just want to, I was a little eager to bring back your past experience for you to get comfortable with those kind of stuff. And now the challenge comes is here. So now we're going to look back at the earlier problems a little bit, and we should have done that. But it worked earlier. That means, so if it works, that means this b squared minus 4ac here has to be greater than or equal to 0 if it worked. But here we've tried a few times, it didn't work. We checked a little further, and so this b squared minus 4ac, okay, this b squared minus 4ac is a value being negative. It's a negative, and so give up on your factoring. We won't be able to find a factor on this. Okay, so now that means no factor. So now the bottom line I'm trying to make here is that even if we forgot to do this in the beginning, because it's not something that we usually do. I take take my word on this, okay? Because when you've learned this in your previous course, I'm sure you've seen this, but it's not always emphasized. It's natural the way it is, okay? Because it's not too common that we run into a quadratic that does not factor. Okay, and so this technique here is easily forgotten. So in case you forgot to do that at first, that's okay. Keep searching for factors. And if we keep failing quite a few attempts, we're going to start thinking of this. And then it will come out. All right. And so now this one here has no factor. So that means because having no factor, this equation here has no solution. No solution. But what's the further impact? So now let me swing over to the graph. Okay, and then I will also explain what no solution means. So if it's simply a quadratic equation, no solution means we cannot find the x value satisfying this equality. Okay, but now in our concept of understanding about horizontal intercepts, what does no solution mean? All right, so on our blank graphing screen right here, on graphing space here, x squared minus x plus 1. This is the graph works. Now it tells the truth. You see, our graph of this polynomial does not hit the x-axis at all. Okay, does not hit the horizontal axis at all. That is what it means by no solution on solving this. Because see, obviously we could not factor. So anytime that we are able to factor, anytime that we're able to factor successfully, then we will be able to end up with some horizontal intercepts. But now we have no factor, consequently meaning no solution. That means for this particular quadratic, we saw that on the graph earlier. This is now no horizontal intercept. All right, no horizontal intercept. Okay, so that's why now this once again reinforced what I said earlier, quite earlier in this part before, right before we got into finding intercepts, horizontal intercepts. See, some polynomial may not have any horizontal intercept at all. So a polynomial given may have intercepts, horizontal intercepts, and may not have a horizontal intercept. This is the case here. This is one among. So it's not always the quadratic that sometimes has no horizontal intercept. It's some polynomial may not have any horizontal intercept at all. Okay, and we will keep getting more and more into that. All right. All right, so now at this point, I would like to make a recap or actually a remark on all of these quadratic, but specifically on all of these polynomials, but specifically quadratics. So let me erase some part of the work that we have had here on the board. All right, so if we're looking back throughout the entire example 8, where I mostly focus, or as a matter of fact, I only focused on the quadratics, then you can see that some quadratic like this one here I brought up in part A, this quadratic was successful for us. I'm using that term successful. We were successful to find the factor of this product, turning that into an x plus 4 in product with x plus 2. And you still saw that here earlier on the board, and I had to erase it to write it in the same line. Okay, and then we came down to that later one being x squared minus 4x plus 4. That was in part B of our example. And we were once again successful with finding the factor product of that. And as a matter of fact, we ending up with 2 identical factors. So that's why I wrote it as the x minus 2 in parentheses squared. Okay, and further we came to just in part C that we finished earlier, just right before this. Then we had that x squared minus x plus 1, and this one here was this one here. I have to put a colon here. No factor. Okay, no factored form. We can't really factor this. And then so we also learned that at least I revealed that solid technique, and you should have learned that technique. But like I said, sadly it might have been easily forgotten because it's mentioned, it's taught, but it's not emphasized enough in any of your prerequisite courses. It's just the way it is, because at the time when you are developing these skills, nobody teaching you can be sure how far you will carry on in your mathematical path right there. And so I'm sure that the technique here worked and was taught, but it's understandable that it was not too emphasized to the point that it's easily faded away in many of you. So that method to check. So see, there were times we got distinct factors, and there were times we got repeated factors in a quadratic, and then there were times we already came to that problem where we had no factor form successfully found at all. And so that decision line was all on the b squared minus 4ac right here. So anytime that we have no factor form right here, it means this b squared minus 4ac has to be less than 0, being a negative quantity. So just see the way how I did that problem right there, and I made a few attempts. So here we would just stick with the usual attempts, and then I say, and then I apply that same with the usual work with these two, and then I made a few attempts. It didn't work out, so I start thinking of this, and then I further confirm that this polynomial here, this quadratic specifically, had no factor form. Okay, so but now that remark I'm about to make is this method here is only solid for a quadratic polynomial, meaning it's a perfect way to decide whether your polynomial, your quadratic polynomial will have a factor form or not. So anytime that b squared minus 4ac is greater than or equals 0, that's where you have that you will have successful factor. Okay, but now for this example 8, I'm not saying that I have covered and revealed all of your skills on the quadratic, especially the factoring method on the quadratic polynomials, simply because in the end this is a pre-calculus course. So I'm only bringing up these quadratics in that purpose to remind you about you have learned these. But now it is outside of this example. I highly encourage anyone learning from this video to review your past material, and I'm sure you must have learned the factoring methods for quadratic polynomial and quadratic equations on other cases, because here I mostly focus my examples on those quadratic polynomials where the leading coefficient here is 1. But when you were learning how to solve a quadratic equation, you were also learning how to solve those quadratic equations where it was, having a coefficient 2 or coefficient 3, anything other than 1 here. And you also learn tricks here and there how you can successfully factor any of those quadratic other than leading coefficient 1. And then, but still, this trick right here, this understanding right here, this checking work right here will work anywhere if you if you highly doubt that your polynomial, your quadratic polynomial will have any factor form. So always remind yourself of this in case that you have made a few attempts, okay, into your quadratic and it's still not getting anything to work out. All right. And so it is important that you review your skill in factoring the quadratic method like that. All right, so now immediately after finishing with example 8, where I focused mostly on the quadratics, and also we've done this example 8 after example 7. Then I can see now, so I can see particularly on the family of all the second degree or degree 2 polynomials, the quadratics as a polynomial. Then let's put the following observation here, and it's also a remark. I feel it's important, that's why I'm writing that in red ink. But it all depends on the more experience you work with, the sooner it's gonna stay with you. Okay, so I don't really force anyone to memorize this remark right here. So it's another remark after what I've made on the other board. So now looking throughout all the problems so far in the world of degree 2 polynomials or the quadratics, then see any quadratic, okay, can have so now I have to start using that term, can have at most, let's experiment that a little bit. Quadratic means degree 2. This one here, we had two factors successfully, and two unique factors, okay, completely different, two factors, and we made that into two successful factors, and then so we came down to two horizontal intercepts, okay, on a degree 2. And then on part B of our example 8, we came down, we got that second degree, again, degree 2 polynomial, but we had a repeated, so in the end we had only one horizontal intercept, okay, as explained here. And we saw that in the graph earlier. So 2, and then 1, and then this one right here that we did in our part C of the example where we had no factor. And then I showed the graph here. Obviously it showed that the graph did not cross the x-axis, the horizontal axis at all. And that's what no factor form also means. And we will also at the end generalize all that idea. But now that means we found no horizontal intercept here in part C, one intercept only in part B, and two intercepts, but no more than that, no more than two intercepts. So start connecting that with the degree here. The degree here is 2. Okay, the degree here is 2. So I'm putting that here as a remark. It seems like it's only for the quadratic, but it starts generalizing an idea that I will bring in later on. Okay, so now these are all the quadratic, and we already found, and as far as the cases, I've done all the cases. So two particular intercepts, only one intercept, or no intercept. So now back on my other board. This remark where I was in the middle of finishing it. Any quadratic, meaning it's a degree 2 polynomial, any quadratic can have at most, okay, 2 horizontal intercepts. All right. And so that's what we recognize right now. That's why I'm calling that as a remark. We only putting it down as an overall observation of what we have done throughout the examples. All right, but now more generally speaking, I would like to enforce throughout example 8 is that we had that factoring method, and that factoring method outside of the world of quadratic function, quadratic polynomial, and stepping to the higher degree, we're still going to stick with the quadratic. We're still going to stick with the factoring methods to find the horizontal intercepts. Okay, and so in example 7 I did earlier was just in a sense that when you already put your polynomial in successful factors where each one of those is a linear, then we're going to isolate it out and solve each linear. And so I purposely reveal your skill how to solve a linear equation. Okay, in example 7 right there. All right, so now let's get into example 9, where we're going to take our understanding. So now the factoring method is really pretty much the only way to algebraically find the horizontal intercepts, okay, if there is any, for a polynomial. So now I'm going to call that example 8. And actually, I just now set the wrong one. It should be example 9 now. Okay, let's find the horizontal intercepts, again, algebraically. Okay, so now allow me to do the following. All right, so let's say we have a polynomial p of x. All right, and given to be, so now x minus 1 in parentheses times x minus 4 in parentheses times x plus 2. All right, in parentheses times x plus 2. And then this is all there is. So what we have here is a polynomial. Okay, and so now the question did not ask for this, but then this is something that we should be able to know in the back of our mind up to this point of our learning. This one here is a degree 3 polynomial. It's no longer quadratic. Okay, and this is, see, the whole example 9 now is the same kind of problem, the similar kind of problem, but now we keep getting into the higher and higher degree of the polynomial over here. So now we're stepping into degree 3 right here. Okay, so now in this entire example 9, I will also get you, anyone learning in this lesson, exposed to the higher and the higher and the higher polynomial, higher degree polynomial. But then we're working with the easier case where the polynomial already came factored, like in this case right here. So you already had your polynomial, it's a degree 3, but it's already in factor form. All right, so that's the intention of this particular example 9 right here. All right, so now to find the horizontal intercepts here, we're going to take the exact experience we have done in example 8 earlier. After we have successfully put our polynomial in factor form, which is what it is right here. So now that think about once we have put our polynomial in factor form, all we do now is, again, I'm going to need to let y equal 0. And letting y equal 0 means this product of x minus 1 times x minus 4 times x plus 2 must be equal to 0. All right, so once we have spent a good amount of time on the quadratic, where we've seen all of that technique, specifically I focus on the method of solving by factoring, then that factoring method is carried over to any other polynomial at a higher degree. And now we're at degree 3, see? And we've had that earlier example showing you how to calculate a degree from a factor form polynomial. Okay, so now once you are equating this factor product to equal with 0 like that, then each one of these is a linear factor. So in that way, we are going to produce 3 separate little equations where each one of them comes from one of these linear factors involved in our overall product here. Okay, so now the first one, well, from the left to the right, the first one is the x minus 1. So x minus 1, this one factor can be on its own equal to 0. Because if it's equal to 0, then it will cause the whole polynomial equal 0. Okay, so now I'm going to add 1 from both sides. Okay, and that produces for me x equals 1. All right. And then similarly, this other distinct, okay, or uniquely expressed right here, this distinct factor, x minus 4, it's now a linear. I can also produce a separate equation for that. X minus 4 equals 0. Okay, and now x minus 4 equals 0, treating that as a linear equation. And that's why we had that example 7 earlier, to re-emphasize, to review your skill on solving these basic one, very basic one. So anytime that we have broken our quadratic into, our polynomial into a successful factor product where it's containing all of these linear factors here, then we can just take each factor, set it equal to 0, set it equal to 0. Okay, so now add 4 to both sides. Okay, that leads me to x equals 4. All right, so we found another horizontal intercept. So when x equal, the logic goes as following. When x equal to either x equals 1 or x equals 4, any of these values will cause this product to equal 0, and consequently our polynomial will equal 0. Okay, and so, but we didn't only have these two, we had even another one. So now how about, now I'm going to produce x plus 2 equals 0, a third separate equation, linear equation to solve for. And then I'm subtracting 2 from both sides. All right, and so now x equals negative 2. Now all of a sudden we found out we got 3 separate horizontal intercepts. All right, so any one of these 3 values, can cause the polynomial here in factor product to equal 0. Okay, and so now let's double check. All right, so now when I said double check earlier, I meant let's confirm that with the result on the graph right here. Okay, to understand a little more clearly, to have a visual understanding. So this is our polynomial. Okay, and so now with this polynomial, apparently it crosses the graph, the x-axis, the horizontal axis at 3 separate intercepts right here at 3 separate intersections right there. And then so one of them is right here at x equals minus 2 as I'm zooming it in, that we can see it. And then we have another one, okay, at x equals 1. And we have another one at x equals 4 right here. Okay, and so this is all consistent. This result graphically observed here is completely consistent with everything we are seeing here on the board. Okay. And so we have found algebraically. So before I pulled up the graph right here, we found that there are three the horizontal intercepts. Okay, so these are the values that caused our polynomial to equal 0. But that also means that's where the graph is going through. The graph is going through the horizontal intercept. Okay, and so let's try another one. Okay. All right, so now I'm going to look at how about part B right here. Let's look at a polynomial. How about I'm going to call it q of x. All right, to equals about x about 2x minus 1. Okay, and then 3x plus 6. Okay, and then x minus 1, and then square. All right. So again, this is another problem that's already made easy for us. It's a polynomial. Now, what degree is this? This is going to be degree 1 here for that linear factor because it's in factor product. So degree 1 for this first factor. And because it had that multiplicity 1 here. And I used that term multiplicity earlier. And then this factor here is a linear factor. Admittedly, it has a common factor here in the two terms, but it's okay. It's, in the end, it's a linear factor for the entire product here. Okay, so now it's degree 1. So together with these two factors, it's degree 2. And then with this last one right here, degree 1, but then with multiplicity 2 right here. So it's going to be an overall of degree 2, degree 1, and plus with degree 1. So your overall polynomial here has to be a degree 4. Okay, it's a 4th degree polynomial. But now, so technically we did have 4 factors, 4 linear factors. 1, 2, and 3, 4. All right, 1, 2, and 3, 4. You see how I tap my fingertips right at that twice because of this factor x minus 1 indeed appeared twice in our factor product right here. And that's why we had that multiplicity 2 there. Okay, so in that way, but now that's just something to understand about the algebra of our polynomial here. Okay, and we didn't really have to do that previously. But now finding the horizontal algebraically, all we do now is we're going to start letting y equals 0. And that produces for us the entire product here, the entire polynomial. And we don't even have to multiply it out because this is already in the easy form for us. We can just easily take this factor product and set it equal to 0. All right, and that's what we're doing right now. And so now at this point right here, I am going to take, just like the earlier example and just like anything that I've done in example 8 right there, okay? And just like the problem earlier in the same example here, I'm going to take each distinct, but now pay attention. We're only going to focus on the distinct factor, okay? So pay attention to the term distinct factor. Only use the distinct factors. So now as far as the distinct factors, this is what I have right here. That one is one of them because it doesn't look like any of the other guys. This one here, now if we're writing that as x minus 1 times x minus 1, then we got 2x minus 1. But only one of the x minus 1 here is a distinct one. That's the whole idea right there about distinct factors. So we really had 4 factors in this polynomial. It's degree 4. But as far as distinct factors, we only had, so one of them is 2x minus 1. So now just like the usual case, I'm going to set that equal to 0. Now I'm going to look at the other distinct factor, 3x plus 6. I'm going to equate that with 0. And I'm going to look at, even though this is, like I said, it's appeared twice, okay? It appears twice in our polynomial, but we only need to look at that as one distinct factor. So x minus 1 can separately equal 0. And so now we have 3 distinct factors, and we have produced for ourselves 3 separate polynomials. All right, and so in that way, now we're going to take our steps solving each one of these for x as 3 separate little equations to solve for. So the first one here, I'm going to add 1 for both sides, okay, and then I'm going to end up with 2x equals 1. So now we know that we're going to divide both sides by 2, okay, and doing all that. So now I'm going to end up, so I'm going to short up space here, so allow me to just write the final answer here. All right, so after doing all that work, my final answer is x equals a positive 1/2. Okay, and now with that one, similar action, similar work, I am going to subtract 6 from both sides, okay, and then giving me 3x equals negative 6. And then I am going to divide both sides by 3. That's the work right there. And so the resulting equation now, so once again, I'm running out of space, so allow me to erase the work I've done temporarily. Because in these days, I mean, I don't even, if it was my student, I don't even require you to write those little steps, because you should be mature enough to know this will give you answer x equals negative 2. Fair enough. Okay, and then with that one right here, x will equals 1. All right, so we found only three separate solutions right here, only 3 separate. Now we call them horizontal intercepts. All right, 3 separate horizontal intercepts. So let's use the graph to confirm our result right here. Okay. All right, so now with my graphing screen right here present, so I'm going to look at this is our graph for 2x minus 1 times 3x plus 6 times x minus 1 all squared right there. All right, so obviously now I don't have to see the whole complete full graph, because whatever it is doing the outside of this viewing window to the lower side right here, that's not important, but at least I do see that my graph is now right here in front of what I can see. It's crossing the horizontal axis. The graph is crossing the horizontal axis, and with the numbers being referenced here at 1, at positive 1/2, and at negative 2. Just consistent with the results we have found right there. And then in a complete full view right here, I hope I can zoom out far enough to show the whole graph. All right, and that's what the graph looks like. Okay. And then when we're zooming out far enough, then that intersection there, that the horizontal intercepts there, is almost very hard to read right there, very hard to see. But that's, once again, we're using the graph here, and we confirmed our graph. We confirmed our work that we have found 3 separate horizontal intercepts there. All right, so now in this example 9 right here, allow me to introduce another problem. All right, so let's now look at the following polynomial, and another one where it's already easily given as a in factor product, in factor form of a polynomial. So how about part C of our example? Let's look at, we have f of x here, okay, being about x minus 2, okay, and then the x minus 1 all squared. Okay, so now we're aware at this point that a polynomial like this in factor form, but we know that a polynomial like this must be a degree 3 like that, and I don't need to constantly spending times on stuff that you already been familiar with. So with a degree 3 polynomial like this, but we only see 2 distinct factors, okay, 2 distinct factors. So just similar to one of those earlier problems we have done right here in this example. Then so now basically, as far as the amount of distinct factors, it's degree 3, but only 2 distinct factors. So on those distinct factors, okay, once again, to find the horizontal intercepts, we're going to let y equals 0. And y equals 0 will lead to x minus 2, okay, and times x minus 1 all squared to equal 0. Okay, and so now once again with these, now I was talking about distinct factors, so these are the only two distinct factors. So in that way, we're going to have one of them is x minus 2 as one of the distinct linear factor. Okay, so x minus 2 equals 0, and then x minus 1 equals 0. Even though x minus 1 as a factor, it has multiplicity 2, but it's a distinct factor, so we don't have to repeat that. We don't have to do that 2 times. So it's just x minus 1, and we're going to start solving for it. Okay, so now I'm going to add 2 from both sides to end up with x equals 2. Right, and I'm going to add 1 for this equation. I'm going to add 1 from both sides and to end up with x equals 1. So now we have found 2 horizontal intercepts for this particular polynomial, but it's a 3rd degree. So I brought this here only in the intention of to have you start observing some nature that sometimes we know the degree of our polynomial, but look at the number of intercepts we have, the number of horizontal intercepts we have. But as far as the work of finding one, as far as just to know how to solve it, how to find the intercepts, I don't think we would need to have this. But I keep putting it here so that you can start triggering up your observation. It can start triggering up your observations about with the known degree. Okay. So this is degree 3. Okay, but we only found 2 horizontal intercepts. Okay, and now another one, and keep getting you comfortable with the idea right there. Keep getting you comfortable with operating with how to find, how to extract, how to find out the horizontal intercepts right out from factor form of your polynomial. So how about this one here? We have f of x in part D of our example. X minus 1, okay, times x plus 1 times x minus 3 and times x plus 2. All right, so another polynomial where it's already given in factor form. Okay, so this time, well, let's just make a good note here. The degree is 4. Okay, it's a 4th degree polynomial. And we have learned already in the earlier example how we can determine the overall degree for a polynomial like this. Okay, so needless to keep mentioning about that. But so now once again, in order to find the horizontal intercept or horizontal intercepts algebraically, then we're gonna start out by we're gonna let y equal 0. And that will consequently lead to the entire product here to be equated with 0. So that leads to x minus 1 in product with x plus 1 in product with x minus 3 and in product with x plus 2 to equal 0. And so now we have produced for ourselves an equation where the left-hand side is completely in factor form and the right-hand side is simply a 0. So now in that way we have done this often enough. So I can just now simply produce 4 separate little equations. So one of them, and each equation comes from one of the distinct factors. Okay, so we've been doing that all over. And so in this particular problem, it's degree 4, and there are no repeats on any of these distinct factors. So each factor each factor appears only once. Okay, so now x minus 1 equals 0, and that's consequently giving me, by adding 1 to both sides, I have x equals 1. The next one here, I'm going to take that factor x plus 1 distinctively. I'm going to set that equal to 0. And then I'm going to subtract 1 from both sides to solve for x. So now x equals negative 1. Okay. The next one here, distinctively, I'm going to take x minus 3 and set that equal to 0. Okay. And then I'm going to add 3 from both sides. Okay. And then that gives me x equals 3. Okay. And the last one here is the x plus 2 as a distinct factor in my product of the polynomial. And then set that equal to 0. And I'm subtracting 2 from both sides. All right, and then now I ended up with x equals negative 2. So with this problem, it's degree 4, and look at the numbers. So knowing how to solve it at this point, like I said, my intention for bringing up these 2 extra problems in homework, in example 9 here, the intention is not to let you keep learning over and over, keep repeating how we can solve for these the horizontal intercepts, but rather I want you to start, putting in your observations in a sense that, hey, I pointed out that this polynomial has this degree, we already know it, and look at how many horizontal intercepts it can produce like that. Okay, so as far as finding the intercepts, we found them all here, and now we want to further look for some consistency between the number of intercepts we found with the degree being pointed out right here. And I'll make that connection in the later step after the next couple problems. All right, so this entire example 9 is simple in a sense that it reinforces the fact that once you can successfully put your polynomial in factor product or in factor form right here, okay, then we can easily find the horizontal intercepts algebraically. And now, so my intention here is to work to find the horizontal intercepts completely without a graph. Okay, and so this example is easy in a sense that the polynomial was already, any of the polynomial here given was already put in factor form. Somebody did that for us, and then all we do is just simply now take each of the distinct factors, okay, and set that equal to 0, and find and then solve each of these distinct factor for 0. And each of those distinct factor must be a linear in the end. Okay, and so now that gives me the number of horizontal intercepts. Okay, or just all of the horizontal intercepts. All right, so now as we keep getting better and better, and as we keep emphasizing to ourselves that finding the horizontal intercepts must strictly, anytime we find a horizontal intercept, we must strictly be able to bring our polynomial somehow, some way, whichever method, but we've got to bring our polynomial into a factor form. And that's the only way where we can identify, the horizontal intercepts. And we can also find out how many intercepts we can end up with. Okay, and so, and at this point we keep, like I said earlier, we keep being more firm about that method right there. So now let me still stay with the kind of problems where we want to use the algebra to find the horizontal intercepts for a given polynomial. But this time, allow me to let the problems become a little more challenging. Okay, and so now I'm going to call that part A. All right, so now the polynomial given here, let's look at, how about x cubed, okay, minus 5x squared plus 6x. All right, it's a degree 3 polynomial. 3 terms or whatever, but degree 3 polynomial, right? And then it's in general form. So what we should have realized at this point is, the example is intended to be the same kind. We algebraically find the horizontal intercepts, but now the situation here is that our polynomial is no longer given in factor form like those that we found in example 9 earlier. So now that means we have to be able to find a factor form for ourselves. Okay, on our own right here, we got to be responsible to find our own factor form of this given polynomial. And this is meant to be similar to example 8 earlier, but example 8 particularly focused on the quadratics, where here we're no longer working with quadratics. See, degree 3, I said that earlier. Okay, degree 3. And so now in this entire example 10 right here, be ready for degree 3, degree 4, 5th degree polynomial, any of those polynomials higher degree than 2. How are we going to find a general way to find a factor product? Okay, so now, before we get started, I only have an advice here. When it gets to degree higher than degree 2, when it gets to any degree higher than 2, like say in this case right here, degree 3 and up, there is no hard rule about how we can find a factor product. Okay, now back in example 8 where we only focus on the quadratic degree 2 polynomial, then we got that solid technique that works anywhere. Okay, and we even had a way to check if our quadratic there will fail to have factor form. But here, when we're at degree 3 and above, okay, then and this is the reason why there has been, like I said, there are people who are the PhDs in this kind of work right here, finding horizontal intercepts for a polynomial. Okay, because there hasn't been any well published rule about how we can find the horizontal intercepts for any polynomial degree 3 and above like that. Or particularly how can we factor something like this? It's still a challenge. There has never been an easy enough the one formula that works anywhere for these kind of problems. Okay, so I brought this thing up. It will be anything I brought up on the board here for problem number 10. It's only going to be a simple problem where with your the amount of understanding at this point viewing this video, you can still carry through. Okay, so now we know our goal, that we have to factor. Okay, so observing the three terms being in front of us here, then I can see that I can factor out the common factor x completely. So factoring out the common factor x, now I'm going to have the x in front of parentheses, and then inside of parentheses I'm going to end up with x squared minus 5x plus 6. Okay, and so when we factor, see, this is not this is not yet the point where we have completely factored our polynomial, because we may be able to factor this even further. Okay, and that's why, and completely factor means, in your factor form, any factor must be a linear factor, like this one right here. It means x minus 0, or just x itself is a linear factor. But now this is not a linear yet, or at least if it's a square, it needs to be an irreducible square, a quadratic that will not have a factor form. That's where we can stop. But now, I mean, you can use your b squared minus 4ac to check, and we can factor this further. Okay, and so now only see, now after isolating out the x here as already a separate factor, now I just now produces two pairs of parentheses, is because I know that I can factor this a little further. Let me clarify this about the b squared minus 4ac. See, how do I know if this, at least I know that now it's a quadratic, so I can work things out similar with example 8 right here. I'm going to start thinking about using the b squared minus 4ac to find out if I can any further factor this x squared minus 5x plus 6 right here. Okay, so scratch work for now on that x squared minus 5x. Okay, and like I said, anyone who's already fluent with this, you can skip this scratch work thing. So b squared minus 4ac, b is negative 5, so b squared is going to be minus 5 squared minus 4 times a is coefficient 1 right here, times 1 times c is positive 6. All right, so that gives me now minus 5, all squared is a positive 25. I'm subtracting 4 times 6, which is a 24. So 25 minus 24 is a 1, which is greater than 0. So anytime your b squared minus 4ac greater than or equal to 0, it's a perfect sign for a quadratic. It's a perfect sign for a quadratic to indicate that your current quadratic can be factored further into linear factor. That's what I've been saying the whole time ever since example 8. Okay, so now on this, now I'm going to start searching for the two factors. So coefficient 1, so now nothing is easier than producing the x variables in the two pairs of parentheses here, and then find the two factors of 6, including signs that sum to negative 5 in the middle. Okay, so those two factors of 6 here, including the sign, they must be negative 3 and 2, and that forms a factor x minus 3, and the other factor is x minus 2. All right, so just now, this is how I see my cubic from start to here. This cubic is factored into x, which is namely the same as x minus 0 times in product with x minus 3 in product with x minus 2. So I have now, at this point, I know that I have completely factored out my cubic polynomial over here. Okay, and so now I'm ready for finding the solution. I'm ready to find the horizontal intercept. Okay. All right, so now on this board, I'm going to start out with that usual method right here. I'm going to let y equals 0. So that will lead to our current polynomial being x times x minus 3 times x minus 2 going to be equated with 0. All right, and so in that way, just like how we've been doing throughout the entire example 8 and example 9 earlier, now I'm going to take that first distinct factor. This is namely x minus 0 equals 0. And so we don't even need to make any further solving. This is already one value. X has to equal 0 in order for this left-hand side equal 0, or in order for our entire polynomial come out equal 0 for the y value. We found one horizontal intercept. Okay, the next one comes out by setting this distinct linear factor, x minus 3 to equal 0. Okay, and so now from this little equation, I can add 3 to both sides, and then end up with x equals 3. All right, and then so here I found x equals 0 as one of them. Now I found another one that made 2 horizontal intercepts. I have a third distinct linear factor here. I'm going to go ahead and take that distinct linear factor, set it equal to 0, and I'm going to add 2 from both sides. All right, that will consequently give me x equals 2. Now I found a third horizontal intercept. All right, so we found x equals 3, x equals 0, and x equals 2. We have found 3 horizontal intercepts. And the work here, we had in this problem, we had to do the factoring method outside. We have to apply our own method, factoring work outside. We did the factoring work. We put our beginning polynomial in general form into factor form here. And then from this point on, we went on and solved for horizontal intercepts by setting each of these distinct linear factors into a little sub-equation to solve for. Okay, let's now look into part B, and so you see where I'm going. But again, as I said, any problem I'm about to put in homework in example 10 right here, it's only gonna be just those where we can, within our reach, within our experience in doing math, we can apply our understanding of factoring methods that we've learned from previous course into putting these into factor form. All right, so now part B, let's look at a polynomial being, how about x cubed minus 8. All right, x cubed minus 8. Okay, it's a short cubic function right there. All right, so now it's in general form, and we need to factor it. So now this is the observation right here. This is observation that I've had right here. It's only 2 terms, and it's connected by the subtraction signs right here. Okay, so x cubed minus 8. So I recognize this 8 here as a 2 cube. The 8 here, I recognize that as a 2 cube. So x cubed minus 8 is the same as x cubed minus 2 cubes. So this is a cubic, but a little more particularly, it's in the form of a difference of 2 cubes right here. Okay, so this is a good experience for anyone. I'm sure you have learned this in your previous course already. But again, I brought this up so that I can enforce your understanding and put that into your experience for the later courses in calculus. You will see this kind of thing quite often. Okay, but we do have a an identity. In algebra, we have a couple identities. So for this particular problem right here, let me introduce this identity, this algebraic identity that you have seen in your previous course, but it's easy to understand that it's faded away already. So if we're looking at the difference between a cubed and b cubed right here. So a cubed minus b cubed. A cubed minus b cubed. The identity I was about to say to remind you is that it can be this difference of two cubes can be factor. Okay, so the first factor easy to remember. It's going to be just the a and b with power 1. Okay, so it started out before factoring it was a cubed minus b cubed, but now we factor that into a minus b. So the power here is just power 1, power 1. Okay. But now in the larger factor here, I'm going to end up with a squared minus ab plus b squared. Okay, so it was proven, and you have seen that in your prerequisite course. If you want to verify that, just simply multiply, distribute out the terms here, and cancel out the like terms. You will end up with end up back to a cubed minus b cubed right here. Okay. But so how does this help our current problem? How does this help our current problem? Yes, I brought up, what I'm trying to say now is that anytime we're having a difference of two perfect cubes, difference of two cubes, we can put that in factor form, and the factor looks just like this. We just simply produce a minus b with power 1, power 1, and then there's a larger product, there's a larger in-out product, there's a larger factor that's formed by a squared minus ab plus b squared. Okay, so in this particular problem that we're having, our problem is a polynomial x cubed minus 2 cubed. Difference of two cubes. A is here, x is a, b is 2. The minus here is just that subtraction sign right there. So now I'm looking at x minus a, and I mean x minus 2. Just like that, difference of two cubes, a cubed minus b cubed is the same as a minus b as one separate factor. And then the other part, see, a squared, correspondingly I'm going to need x squared, because x is playing in the role of a, minus, okay, now I'm going to go, see, this is b, this is a, so minus ab, this is 2x, okay, and now I'm going to add, so b squared. But b is 2 itself. Now be careful with that minus right here. This subtraction was part of the formula of the identity. So it's always there. But now in this part right here, it's plus b. So b is the 2 itself. Okay? And so now I'm looking at 2 squared. But 2 squared here is a 4. So x minus 2 in product with x squared minus 2x plus 4. Okay? So I'm not saying anything about whether we can factor this any further or not. We'll get to that later, but at least immediately with this difference of two cubes, of two perfect cubes, I can already apply that identity right here. All right. And so this identity can be found anywhere over the web resources. So, outside of my own lecture, you can just hop on to Google and type it in difference of two cubes. It will pop out this identity for you again. Okay, and right here, and I said this was introduced already in your prerequisite course, and here I'm just reminding you and kind of enforce how it can be used, how it can be useful for us here in our problem. Okay, so we factor that into this. All right. So now back into this problem. Yes, admittedly, f of x, the polynomial here, can be factored as x minus 2 in product with x squared minus 2x plus 4. But so similar to part A we have done earlier, we want to find out if we can completely factor, meaning because right now, yes, that is a linear factor, but this is not a linear factor. This is a quadratic factor because it has that square right there. So we want to know if we can factor this even further into some two distinct factors. Okay, so now before we attempt doing that, you can even spend a few attempts and experience for yourself that we're gonna fail. Okay, and so now let's quickly check with the b squared minus 4ac, b squared minus 4ac. For this particular quadratic, a is 1, b is minus 2, c is 4. So b squared minus 4ac is the same as a minus 2 all squared minus 4 times a, which is 1, okay, times c, which is 4. So that gives me, this is a 4, positive 4 minus 16, which is a negative 12 here. So b squared minus 4ac is indeed a negative value, which is a perfect sign indicating that this quadratic can no longer be factored. It's already in its irreducible form. Again, this is a very effective method or technique, whatever you want to call it, but very effective methods anytime to work on a quadratics to indicate, to tell yourself, to expect for yourself whether we can factor this quadratic or not. Okay, factor the quadratic into the linear factor. So now we know that we can no longer factor this into linear factor, and this is where we said we have completely factored out our the polynomial from the start to here. All right. So now, to find horizontal intercepts, I'm going to say let y equal 0. So that will consequently lead to this product, x minus 2, in product with x squared minus 2x plus 4. Okay, must be equal to 0. All right. But now, I have two distinct factors, but the only linear one is here. X minus 2 equals 0. And so that consequently, now add 2 to both sides, that consequently leads to x equals 2. So we found one horizontal intercept so far. And so let me clarify a little further about this x squared minus 2x plus 4 can no longer be factored into the linear product, and what would be the consequence of that? I have explained earlier in one of the problems in example 8 that when a quadratic can no longer be factored into the linear factors, and that means this particular quadratic itself has no horizontal intercept. And that's the reason why we can completely disregard. Because think about x squared minus 2x plus 4. If we're setting that equal to 0, it won't be true. So we won't even have to worry about that. Another way of saying this entire product right here, or this entire polynomial right here, has only one horizontal intercept. That's the logical argument of that. All right, and so now it's a cubic, but we found only one. This is degree 3. We found only one horizontal intercept. All right, but that's how we've done, that's how we factor, and so I purposely brought up a few of these. I said that they're easy because they're all within the experience you have already seen from your past courses. Okay, but see, there has been no hard rule about what's the solid method. You see, some problem we have to go by factoring out common factor. Some other problem we have to apply some identity. Right there, there's no hard rule about, or there's no one fixed formula about what we can do to solve the problem. Okay. All right, and so now in this one, allow me to introduce another one that's still within what we can reach within the experience we have seen from our previous course right there. All right, so how about we are looking at f of x equals x to the 4th minus 2x squared plus 1. All right, x to the fourth minus 2x squared plus 1. It's a fourth degree polynomial, degree 4, and be ready for degree 5 and anything like that. Okay, but sadly there's just no hard rule about, well, we know we have to factor. Okay, but there's no hard rule about how we can factor any of these polynomial with degree 3 or higher. And so what I observe here is that it goes, now the x to the fourth here can be seen for you guys, for anyone viewing this lesson, being a pre-calculus course. You have already seen enough algebra, so x to the fourth can be, as an experience, can be seen as, can be understood as an x squared square, x squared square. Okay, I wrote that in a reason. X squared square, there's this x squared and that's x squared. Okay, and so now that's what my intention is. I'm going to write that as an x squared square minus 2x squared plus 1. Okay, and so now it's also a method that was introduced in the earlier course, but sadly is not too emphasized. So here I'm just reminding you that you also have this option to handle your polynomial sometimes. So I can use a variable, an external variable u, for example, to be x squared. Okay, so u equals x squared. So now if u equals x squared as a substitute right here, then our polynomial becomes, see, x squared now is substituted by u. So u squared minus, okay, 2u plus 1. There's an advantage of doing this, extra substitution, because now once we've done that substitution, we brought our polynomial into a polynomial in terms of u, and it's now a quadratic. And with this quadratic, it's making it so much easier to factor out. This, as a matter of fact, in our, and I'm sure you have seen this term already in your previous course, when you see something like this, we refer to that as quadratic-like. Okay, in case you forgot, in case that that term has faded away in you, this is called quadratic-like. Okay, quadratic-like polynomial. It goes 4 and 2 and constants, because when we substitute the x squared away, then we're going to end up with a quadratic. And now with this quadratic, now we can check, and we can check with the a squared minus 4. I mean, we can check with the b squared minus 4ac right there to find out if we can factor. Okay, so now I want viewers or students who are learning from this lesson to go ahead and double check on that to see if we can factor this quadratic in terms of u right here. All right, so now provided you have already spent some time checking, yes, we can factor this. So the factor product here is going to be the following. This is going to be a u minus 1 all square. A u minus 1 all square. All right, but then everything I'm doing here is all sudden we change track to u variable. That looks a little inappropriate. All right, so here's how we make our way back. Well, u was x squared. U was a substitution for x squared. So that means we're looking at x squared minus 1 all square. X squared minus 1 all square. Okay, but x squared minus 1 all square, well, it means we're looking at, so now all of a sudden we realize, now in terms of x as the variable, then we did not completely factor. We put our polynomial at start, the fourth degree here, into some factor form already. For this is precisely speaking x squared minus 1 times x squared minus 1, two identical factors. But each one of these, indeed, we can factor out even further. X squared minus 1. The other x squared minus 1 is here. Think about that. Okay, so this is a quadratic in terms of x. This is a quadratic in terms of x. Okay. Just earlier I was introducing the difference of two cubes. You must have learned this too. The difference of two squares. And I believe there are more students remember about the difference of two squares. For some reason it's used a lot more often than the difference of two cubes. So once I reintroduce this, once I remind you about this, it will click immediately. So a squared minus b squared, the difference of two squares can be factored into a minus b with linear factor, okay, times a plus b, in product with a plus b, okay. So now in our situation here, think about the x squared minus 1. This one here is the same as 1 square as well. Difference of two squares. All right, so difference of two squares now we can use this particular identity right here to factor it, to put that in factor form. So now x squared minus 1 squared is the same as x minus 1 times x plus 1. X minus 1 times x plus 1. Okay, so why is this useful? That is because, see, x squared minus 1 and another x squared minus 1. So now, in other words, we can continue factoring each one of these quadratics as following. This first one right here is the same as x minus 1 times x minus 1. Times x plus 1. And then the next one is another x minus 1 times x plus 1. It takes a little time, but believe me, once you practice enough, these things will come a lot faster. Okay, x minus 1 times x plus 1 again. So as a matter of fact, now all of a sudden we realize there's a repeat. This is really together these two factors. They are identical factors. So we can rewrite. So in my left board space here, okay, let's put it all together. So the f of x now can really be factored, the polynomial from the beginning can be factored as x minus 1 all square times x plus 1 all square. So now these are all in linear factors, and each one of these has some repeats, okay, has some multiplicities. All right, and now at this point we affirm that we have successfully factored our polynomial from the beginning. This was our originally x to the 4th minus 2x squared plus 1. All right, well, it took some time, but I purposely brought this up to remind you some of the tools you have learned before, and now it's time to use it. Okay, it's time to use it. So now we're finding the horizontal intercepts. Okay, so in that way, y equals 0. We're going to let y equal 0. And now with our polynomial currently in factoring product right here, that leads to x minus 1 all square times x plus 1 all square must equal 0. Okay, and so in that way now I'm just like any of the earlier problem. We got some multiplicity on each of our factor here, but in the end we only have two distinct linear factors. So very similar to what we have done earlier. I'm going to take the first distinct linear factor, which is the x minus 1, set that equal to 0. Okay, and I'm going to add 1 from both sides to solve for x. So here I'm ending up with x equals 1. We have found one horizontal intercept. Okay, and then let's move on to the next distinct linear factor. X plus 1, I'm going to set that equal to 0. Okay, and so now I'm going to subtract 1 from both sides, and that's ending up with x equals negative 1. We have found a second horizontal intercept. Okay, so in the end, our problem from the beginning start out with 4th degree 4 polynomial. This one at start. Okay, and then I was explaining that I saw this as a square, the 4th degree right here. I saw that as a square of a square, and so now this is why I reminded you about that term you should have picked up from your previous course. This is here a quadratic-like polynomial, and so to make it easy, we're gonna just do a substitution with an extra variable here. So to let u equals that x squared. And so now we perfectly brought that into a quadratic, and then we factor out that quadratic. But then that quadratic here was in terms of u. So we brought back that variable x right there. So it took some time, but like I said, I've shown all of my explanation already. So keep rewinding if you need to see my explanations again and again. Okay, but as you keep going over this, you will get better at that. So in the end, this whole x to the fourth minus 2x squared plus 1 was completely factored down to something like this. And this is where, even though with a fourth degree polynomial, we ended up with only 2 horizontal intercepts. Okay, only 2 horizontal intercepts. All right. All right, so now let me bring you into a short example. I call that example 11, but just a short one, and we don't have to do part A, part B, or part C or anything like that, just one problem. And the worded instruction is going to be slightly different. So let's now call that example 11, okay? So we still want to find a horizontal intercept. Just find the horizontal intercept, okay, or multiple. That's it, okay. But the problem we have here, f of x equals, how about x cubed minus 4x squared plus x plus 1, for example. X cubed minus 4x squared plus x plus 1. And to be honest with anyone viewing this lesson, I came up with this completely random as a random creativity thing, completely out of my own creativity. No plan ahead, okay? No plan ahead on this one for here. So, does that mean I am expecting students or viewers to be able to factor this out on your own? Because it looks like I've led you so far into that experience that we gotta put thing into factor form and factor form and factor form. So what about something like this, where now even I, to be honest, even I feel very challenging to factor something like this. It's just a cubic, okay, it's just a cubic. But now, like I said, there has never been a hard how-to rule about how-to rule to factor out something like this. Okay, so the worst case is here when it takes forever, or when it's nearly impossible to factor out, because like I said, even I look at this, look at something like this, I just want to give it up, okay, because the factoring on something like this, it's not so easy. So when that case comes, the instruction is only saying find a horizontal intercept, but did not indicate algebraically. It did not indicate that we have to do that with any algebraic method. And so we have one last method right here. It's not the best, okay, but it's definitely a working one. It's not the best. I'm saying it again. It's not the best method, because the algebraic method is the best. But this one here, because we are not able to use the algebraic methods, we're not patient enough for that. We already knew that we'll have maybe some kind of intercepts, but factoring out is going to take forever for something like this. Okay, so let's find what's that not the best solution, but the working solution. I'm going to turn over to the graph. All right, so on my empty graphing space right here. Okay, so all right, so now here's my graph for this function. There we go. Okay, the graph for this function. All right, and so now looking at this graph, see, that's why, like I said, now when we're looking at the graph, the best thing we can do is to estimate. So this point right here is right about when it intercepts. So gladly my graphing utility is strong enough to give a good enough, decent the estimation. So how about I have one, so seeing the graph, we know that we will have 3 horizontal intercepts. Okay, one of them is at negative x equals negative 0.377. The other one is at positive 0.726, and another one is at 3.651. And this is about the best we can do. So my point of bringing up this short example is that in case where factoring method seems to be completely out of choice, to be completely not a choice anymore, right? Not a working choice anymore, because it takes a lot of time and hopeless, becomes so hopeless, then we're going to turn to using the graph. So here we were still able to find the horizontal intercept, but through the graph right here. So the best thing we can do is just to estimate. All right, so now my estimate shows about, so from what I see here, it was about, right, and that's all I can say, it was about negative 0.377. That's one of them that we found, and it's still there on the screen. Yeah. Another one that I found was x equals about, right? X equals about 0.726, okay? And then the last one here is x estimated about 3.651. 651. All right, so the graph obviously showed us there are 3 horizontal intercepts, okay? But then precise value, that's why I said, you know, it's only a working method, but it's not the best, because the best we can do here is just to estimate. It's the algebra method will give us the best precise answer, but here we only can estimate through our own eyes right there by looking at the graph. Okay, so that's how we did the number 11 right there, example 11, for a polynomial, generally representing the case where we don't want to do factoring anymore. Okay, and that's the it's not the best, but it's a working solution. All right.